Here's a question. Why do you exist? That's not a philosophical question. It's a physical one. The Big Bang produced equal amounts of matter and antimatter, and when the two touch, they annihilate. So in theory, nothing should exist. No rocks, no stars, no you. But here you are, which means somewhere the equation broke. And whoever understands that breaking point will understand why the universe exists at all. Let's start with what antimatter actually is. Because most people think it's science fiction. It's not. It's one of the most thoroughly tested, most precisely confirmed predictions in all of physics. And we make it. Right now, in laboratories around the world, humans are creating antimatter particle by particle. The PET scanner at your local hospital uses it. The positron, the antimatter counterpart of the electron, gets produced, travels a few millimeters, collides with an electron, and they both vanish in a burst of gamma rays. That's how the image forms. Antimatter is real, measurable, useful, and it should have destroyed everything. Here's how we found it. In 1928, a physicist named Paul Dirac was trying to write one equation. Just one. An equation that combined quantum mechanics, the physics of the very small, with special relativity, the physics of the very fast. The electron needed to obey both. Dirac wrote the equation. It worked. It described the electron perfectly. But there was a problem. The equation had two solutions. Not one, two. The first solution described the electron as we knew it. Negative charge, tiny mass, spinning in a specific way. The second solution described something else. Something with the same mass as the electron, but with positive charge and negative energy. Dirac stared at this for a long time. He thought he'd made a mistake. He hadn't. The equation was telling him something real. In 1932, a physicist named Carl Anderson was photographing cosmic rays, high-energy particles raining down from space, when he saw a track in his cloud chamber that curved the wrong way. Curved exactly the right amount for an electron, but going in the opposite direction, positive charge, the same mass as an electron. Exactly what Dirac's equation had predicted. The positron. The first antimatter particle ever observed. Anderson got the Nobel Prize. Dirac got his too. And physics got a problem that still hasn't been solved. Because here's what the discovery of the positron really meant. If the electron has an antimatter twin, so does the proton, so does the neutron, so does every single particle in existence. Every particle has an antiparticle, opposite in charge, otherwise identical. This isn't speculation. We've confirmed it for every particle we've ever found. Which means that when the universe began, when the Big Bang released an enormous amount of energy, it should have produced matter and antimatter in equal quantities. One proton for every antiproton. One electron for every positron. Perfect symmetry. And then they should have met and annihilated. All of them. Every single particle of matter meeting its mirror image, the two canceling each other out in a burst of pure energy. The universe would have been nothing but light. No atoms, no molecules, no planets, no people. Permanent, silent, absolute nothing. Let's make the annihilation concrete. Because the word annihilation sounds dramatic but abstract. Here's what it actually means. Take one electron and one positron. Bring them close enough to touch. Both disappear. Completely. No trace. Instead, two gamma-ray photons fly off in opposite directions, each carrying exactly the energy corresponding to the mass of one particle. E equals mc squared, in both directions. The particles are gone, converted entirely into energy. This isn't a chemical reaction where atoms rearrange. It's not like burning where molecules break apart. It's total conversion. Matter into pure energy. Both particles simply cease to exist as matter. Now scale that up. In the first fraction of a second after the Big Bang, the universe was a dense, hot plasma of particles and antiparticles, constantly annihilating and recreating. The temperature was high enough that energy could spontaneously convert back into particle-antiparticle pairs. Creation and destruction in constant balance. But as the universe expanded and cooled, the temperature dropped below the threshold for pair creation. New pairs couldn't form anymore. The existing ones just annihilated. All of them. Every proton finding an antiproton. Every electron finding a positron. The entire inventory of matter and antimatter mutually destroying itself. Except, by that point, there was one extra proton for every billion antiprotons. One extra electron for every billion positrons. When the music stopped and everyone had found a partner, there were a billion survivors with no match. Those survivors are us. The entire visible universe, 400 billion galaxies, each containing hundreds of billions of stars, is the leftovers from a process that destroyed nearly everything. There's one more thing worth understanding, because it comes up when people think about this. Where did all the antimatter go? Not just why was there more matter, but where is the antimatter now? The answer is, it's gone, converted into photons. Those photons are still here. The universe is filled with them. The cosmic microwave background radiation, that faint glow of microwaves that fills all of space uniformly in every direction, is partly the afterglow of all that annihilation. When you look at the CMB, you're looking at light that was produced, among other things, when matter met antimatter and both ceased to exist. The antimatter didn't go anywhere mysterious. It converted into energy, and that energy is still in the universe, just in a different form. You're swimming in the afterglow of the destruction that made your existence possible. This also means something about the geometry of the cosmos. If matter and antimatter had annihilated completely and evenly, the CMB would be perfectly smooth. But it's not quite smooth. There are tiny fluctuations, temperature variations of 1 part in 100,000. Those fluctuations are the seeds of everything. The slight differences in density that, under gravity, grew into the first stars, then galaxies, then galaxy clusters. The large-scale structure of the universe we see today traces back to those fluctuations. And those fluctuations trace back to the asymmetry. One extra particle in a billion, distributed unevenly, creating the density variations that gravity could amplify over billions of years into the cosmic web of galaxies we inhabit. But that didn't happen. You're reading this, which means something went wrong, or rather, something went right. Somewhere in the first second of the universe's existence, the balance tipped. Very slightly. For every billion antiprotons, there were 1,000,000,001 protons. For every billion positrons, 1,000,001 electrons. One extra in a billion. That's it. That tiny imbalance, one particle in a billion surviving the annihilation, is the entire observable universe. Every star, every galaxy, every atom in your body. You are made of leftovers. You exist because the universe was slightly, almost imperceptibly, asymmetric. The question is, why? In 1967, a Soviet physicist named Andrei Sakharov laid out exactly what conditions would have to be true for this asymmetry to happen. He identified 3 requirements. First, some physical process must be capable of creating more matter than antimatter in the first place, a violation of what physicists call baryon number conservation. Second, the laws of physics must treat matter and antimatter differently, not just in charge, in every way. This is called CP violation. Third, the universe had to be out of equilibrium while all of this happened, so that the asymmetry couldn't just reverse itself. All 3 conditions had to be met. And all 3 have to leave traces we can still detect. The second condition is where things get strange. Are the laws of physics actually different for matter and antimatter? It seems obvious they should be the same. That's what symmetry means. But in 1964, 2 physicists named James Cronin and Val Fitch discovered something remarkable. They were studying the decay of a particle called the kaon, a short-lived particle produced in particle accelerators. And they found that kaons and antikaons don't decay in exactly the same way. The matter version and the antimatter version behave slightly differently. Not very differently, but measurably differently. The universe does treat matter and antimatter differently. It always did. Cronin and Fitch won the Nobel Prize in 1980. Physics had confirmed Sakharov's second condition. This is the moment to pause, because what Cronin and Fitch found sounds like a small technical detail, some obscure particle decaying slightly differently. It isn't. What they found is the reason you're alive. The fact that kaons and antikaons decay at different rates is part of the same asymmetry that, in the first fraction of a second after the Big Bang, produced one extra matter particle for every billion antimatter particles. Without that tiny difference in decay rates, without that minuscule violation of the symmetry between matter and antimatter, there's nothing. Just light. But here's the problem. The CP violation we've measured, in kaons, in B mesons at the Babar experiment in California, and the Bell experiment in Japan, is real, confirmed, but it's not big enough. Not nearly. The asymmetry we measure in these particles is orders of magnitude too small to account for the 1 in a billion excess of matter that produced the universe. The numbers don't add up. We've confirmed that CP violation exists. We just haven't found enough of it to explain why anything exists. Think about what that means. We have found the mechanism. We know the type of process that must have caused the matter-antimatter asymmetry. We just can't make it add up. There's something missing. Some source of CP violation we haven't discovered yet. Some process that happened in the first second of the universe that we haven't reproduced in any laboratory. The universe did it. We can see the result. We're living in it. But we can't fully account for how. There are experiments running right now trying to find the missing piece. The LHCb experiment at CERN, the Large Hadron Collider Beauty experiment, studies the decays of B mesons with extraordinary precision, looking for differences between matter and antimatter behavior that are bigger than what the standard model predicts. So far, hints. No definitive discovery. The T2K experiment in Japan fires neutrinos, the ghost-like particles that barely interact with anything, across 295 kilometers of rock, looking for a difference between neutrinos and antineutrinos. Early results suggest there might be one. CP violation in neutrinos. If confirmed, it could be exactly what's been missing from the calculation. Neutrinos are worth stopping on. They're strange particles. No electric charge, almost no mass. They travel through the Earth as if it isn't there. Billions of them pass through your thumbnail every second. You never feel them. But there might be something deeply important about them. Because the neutrino is the one particle type where the matter-antimatter difference might be large enough to matter. If neutrinos and antineutrinos behave differently enough, if their CP violation is big, that difference could have seeded the asymmetry that produced everything. You might owe your existence to the behavior of a particle you can never feel. There's another possibility. Something more radical. The asymmetry might not come from CP violation at all, or not only from it. It might come from a process we've never observed. In the early universe, conditions were extreme beyond anything we can reproduce. Temperatures of 1 trillion degrees, energy densities that make modern particle accelerators look like toys. In those conditions, processes might have occurred that violated baryon number conservation, that literally created more protons than antiprotons from scratch, in ways that leave no trace in our current experiments. Baryogenesis, the technical name for this process, might have happened through electroweak interactions at the moment the Higgs field settled into its current state, giving particles their masses. The universe changed phase, like water freezing, and during that phase transition, the accounting rules for matter and antimatter broke down temporarily, just long enough to tip the balance. Wait, because that brings us to something worth sitting with. The Higgs field. You've heard of the Higgs boson, found at CERN in 2012. But the boson is just a ripple in the field. The field itself fills all of space. Right now, everywhere you are, the Higgs field has a specific value, and that value is what gives electrons and quarks their masses. Without it, all particles would be massless. All particles would travel at the speed of light. Atoms couldn't form, chemistry couldn't happen. The Higgs field is what makes matter possible. And the moment it settled into its current value, a phase transition in the early universe, might be precisely when the matter-antimatter asymmetry was locked in. The mechanism that gives you mass might also be the mechanism that ensured you would exist at all. We don't know if that's what happened. The honest answer is, we don't know what caused the asymmetry. We have the Sakharov conditions as a roadmap. We have confirmed CP violation in kaons and B mesons as a proof of concept. We have hints of CP violation in neutrinos. We have theoretical models for baryogenesis during the electroweak phase transition. But none of it adds up fully. The asymmetry we can measure is too small. The processes we can confirm are insufficient. There is something missing. Something that happened in the first second of the universe that we haven't found yet. And here's the part that tends to stay with people. Consider what you're made of. Atoms. Each atom, a nucleus of protons and neutrons, electrons orbiting around it. Each proton, 3 quarks. Those quarks are matter particles. They are the specific type of particle that won the annihilation battle in the first second of the universe. You are made of survivors. Every single quark in your body is a particle that had a counterpart, an antiquark, that it annihilated with. But there was one extra. 1 in a billion. And that extra one, and the extras like it, survived, cooled, combined into protons and neutrons, then into hydrogen and helium, then into stars, then into heavier elements forged in those stars, then into you. You are what's left after the antimatter war. And the war was almost total, almost perfect annihilation. The margin of survival was 1 part in a billion, and that was exactly enough. That's not a metaphor. That's the actual physics. The universe nearly canceled itself, completely. What survived? Everything you can see, touch, weigh, measure, is the tiny residue of an imperfect annihilation. And we still don't know why the annihilation was imperfect. If it weren't, if the symmetry had been exact, if matter and antimatter had been produced in perfectly equal quantities and destroyed each other completely, the universe today would be a thin, cold, expanding sea of photons. No stars, no planets, no chemistry, no time long enough for complexity to arise. Just light, forever, spreading thinner across an empty universe. That's what perfect symmetry looks like. What you're looking at when you look at your own hand, what you feel when you breathe in, is the physical evidence that the symmetry was broken. Slightly, in exactly the right way, at exactly the right moment. The scientists at CERN are looking for the rest of that evidence right now. Every B meson that decays inside the LHCb detector, every neutrino that flips its type during the T2K experiment, each one is a test of whether the missing asymmetry is where we think it might be. We haven't found it yet, but we know it's out there. It has to be. Because the alternative is that the universe shouldn't exist, and you do. If you want to leave a comment, here's the question. Which part landed hardest? The idea that equal matter and antimatter should have left nothing? The 1 in a billion survival rate? The fact that we've confirmed CP violation but can't make the numbers add up? Or just the image of every quark in your body as a survivor from an annihilation that almost worked? Leave it below. And if you want to keep following questions that seem simple until you pull on them, subscribe. That's what this channel is for.